सहना भवतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So far we have seen design of circuits, sometimes even subsystems, using different types of ICs, small scale integrated circuits, medium scale integrated circuits and large scale integrated circuits. In the case of combination logic, apart from gate implementation, we have also seen how to implement circuits using multiplexers and programmable devices. In the case of sequential circuits, we talked about flip-flops, counters and registers. We had taken some examples, sometimes examples such as code converter or pattern generation, pattern recognition, looking for a particular pattern. We did not really, these were simply examples to illustrate various design techniques using combination logic building blocks like gates and sequential logic building blocks like flip-flops, and also to implement, to illustrate the concept of using MSIs and LSIs for implementing these circuits. Some of them we can call them as subsystems because of their complexity. But in a digital system design, a wide variety of most of these devices today, most of the applications today in electronics are digital systems, be it a traffic light controller or a controller to elevate the controller to control the movement of a lift or an elevator, or a chemical plant, control a chemical plant flow of fluids and controlling of levels of various fluids. It could be an automotive electronics, it could be a simple home appliance like washing machine or remote control of a TV. It can be a little more complex device such as flight control in aircraft or for flight simulation or for rocket launch, or it could be a simple computer or a calculator. Whatever is the system, the complexity appears to be formidable. When you are asked to design, let us say, a huge system, a digital system, you will be overwhelmed with the complexity of the system. But if you think for a while, all the tools that we have developed in this course so far, basic implementation of combination building blocks using SSI, LSI, MSI components, basic implementation of sequential building circuits, sequential circuits using building blocks such as flip-flops and registers. These are the same techniques we will be using again and again. We talked about minimization using corner maps for gate reduction, then we talked about multiplexer based design. We also combined the combinational and sequential designs together in a single IC, like a programmable array logic device, where there is scope for putting a combination part and a sequential part in the same circuit. So, really when a system is given to you, if you start analyzing the requirements, if you identify clearly the specifications, if you identify clearly the input signals available and the output signals required, we must be able to come up with a state graph, and once you have a state graph, you know how to implement it. Of course, it may become very large problem with a large number of states, and we have to go for some techniques like CPLDs and FPGAs, but conceptually we have most of the tools, most of the techniques available to us now. To illustrate this point, we are going to look at some of these examples, how it is important to understand the design requirements, how it is possible required to understand fully the system you are going to design, the input requirements and output requirements, and how these can be met easily, and how to build them using these components. So, you have to identify the circuit, the system requirements very clearly before you can choose the components. Once you choose the components, you should know how to use them properly, then the design becomes straightforward. This approach is called top down design approach. Take an example of a computer design. A computer looks formidable when I ask you to build a computer, a calculator. But on the other hand, if you start thinking of the computer as a collection of building blocks such as arithmetic logic unit, memory unit, input unit, output unit, then functionally understand each one of those, and look at the arithmetic logic unit as an example. After all, it contains arithmetic and logic functions, and we know how to implement arithmetic functions. It can be gate oriented, it can be multiplexer oriented, it can be MSI for adder or MSI for adder subtractor. Likewise, logic functions we know how to implement, and we should know how to combine in the same block an arithmetic and logic function. So, when you go top down and down, you will be able to identify, break a system into subsystems, a subsystem into units, functional units. Functional units can be either available, can be available components which are available readily as SSI or SSI, MSI or LSI, or we build them using SSI and MSI. And then of course comes the interconnection and controlling of them. That is where the state graph comes into picture. How do you control what is the sequence of events that take place, and how the signals from one unit feed into the other next unit, and how the output of the second unit affects the third unit, and so forth. So, it is clearly the understanding of the specification of the problem and drawing a proper state graph. Once you have that, rest of the design falls in place, and we will have the soon realize that we have a power, a power to design a whole range of digital systems. We are going to illustrate this concept by means of two examples. One is a simple example, the second one will be slightly more involved. I will tell you why it is slightly more involved, not because it is bigger in size, because it is a slightly different concept we are going to talk about there. In the first example, we will consider a traffic light controller. We know that traffic lights are installed in road junctions, and they come with a variety of features. It could be a simple two-way intersection where one street is red, one street is green for a while, and the other street is red, and then after some time they switch. Then there can be a street with turn signals. So, there has to be, in addition to main street and side street signals, we need to have a turning signal. When you have a turning signal, you have to make sure some traffic is allowed in a certain direction, not allowed in certain other direction, because it will collide with the traffic coming from the opposite direction. We can add to that some pedestrian crossings. There are several ways in which you can control this timing of these signals. You can have a set timing, for example, main street signal will be on for a while, let us say 2 minutes or 1 minute, and side street signal will be on for 30 seconds, and then it will repeat. Or you can have a timing based on the requirement. Main street will be on green and side street will be red all the time until there is a traffic detected in the side street. That can be done by means of sensors or switches. You can put some light switches or sensors in the side street. Whenever there is a need, the side street can go red, can go green, rest of the time can stay red. And then you have to make sure that this doesn't happen very frequently, because you don't want to interrupt the main road traffic very frequently. So you may have to put a condition that if a side street traffic occurs, if traffic occurs in side street, and if you are not switched if the main street has been on for at least for a given amount of time, then and only then it will be recognized and the lights will change. So you can go on inserting conditions and making it more and more complex. And then you can have a pedestrian switch, as I said. Sometimes the traffic is so fast and the pedestrians are left with no option to cross the street safely. So there you can install some pedestrian switches, and once in a while, again not too frequently, once in a while you can detect the pedestrian switch, and if it is on, the traffic can be halted to let the pedestrians cross. So some of these examples, some of these features can be built in, and you can decide on the timing, sequence, etc. And this will be illustrated by a simple example we will take. So in this class and maybe a subsequent 1 or 2 classes, we will talk about system design. And the first system we are going to design is a traffic light controller. To make it simple, as I said, I am going to assume an intersection of a main street and a side street. This street I am calling a main street, where traffic is allowed in both directions, and this street is a side street. Normally, main street traffic is allowed. That means there is a green in both directions, and the side street can take a left turn here from main to side or side to main left turn. That means even when the traffic is on here, one can make a turn from this street to this street, or from this street to this street, of course safely, making sure that you don't collide with the oncoming traffic from this direction. So this I will call this one state. There are several states in which this lights can exist. The first state in which it is found is green on this side, green on this side. This traffic is not allowed, the turning signal is red. Side to this also, this see a turning can happen from main to side or from side to main. Both signals will be red normally. So to identify this, I am going to call these lights, M1 is a light for the green, M1 is a light for traffic from left to right on the main street. M2 is the light for traffic from right to left of the main street. M1 and M2 are the normal main street lights, both are normally on, green. MT is the turn signal for turning from the main street into the side street, MT, M turn, main turn, that means turn from main. And S is the side street signal, which is used to turn from side into main. So normally M1 is green, M2 is green, M2 is red, S is red. That is why I wrote here M1 green, MT red, MT is the turn signal, M2 main to second signal of the main, green, SR, side is red. This is the first state, which is usually available state. As I said, at this point I can decide to wait for a traffic condition to be detected, or I can go for a timing. So let the traffic be on for a while. To make this problem simpler, I am going to make it as a time dependent change in lights rather than a sensor dependent. That means after a while, the time for which the main is green is called TMG, I am calling TMG. After the time t mg has elapsed, that means time t for which the main is green, after that interval of time we have to prepare to let the main street traffic go into the side street. That means we should prepare to take MT to green, but I can't abruptly do that, because in order to do that I need to make M2 red. I can't make M2 red from green suddenly, because that will create problems for the people who are traveling with a fast rate, high speed vehicles. So, you go through an intermediate light called amber or red or yellow, some people call it yellow, some people call it amber. So, this is the disposition of the lights. We have a green light, yellow light and a red light in each of these. Each of these lights, when I say M1, M2, MTS, each of these are fitting with 3 independent lights, green, yellow, red. So, before you make this turn, I need to make M2 green, I am sorry, M2 yellow. So, M1 continue to be green, MT will be continuing to be red, MT will continue to be red, side will be continue to be red, but M2 will change from green to yellow. That is my second state. My second state will have M1 green, MT red, M2 yellow, side red. That means I am preparing for the turning from main street into side street by switching on the turn signal as green, but not immediately, but after a while. Again the yellow light, how long should I keep it? That depends on the traffic flow conditions and the speed of the vehicles, etc. Normally the main street yellow has to be longer than the side street yellow, because main street traffic is faster compared to side street traffic. A vehicle which is coming at a faster rate needs more time to stop. So, yellow for the main street should be longer than yellow for the side street, but we will not go into all those nitty-gritties. We can always incorporate all these features changes later on. So, to make the problem, as I said, to keep its specification simple, I am going to call it Ty. Ty is a yellow, the time for which any light is going to be yellow, whether it is a main light, side light, turn light. Whichever is the light which is going to be yellow, the time for which it will be yellow before it becomes red, we will call it Ty. So, after Ty, from here state to S2, after the elapse of Ty, we go to the third state. In the third state, I have a main continues to flow, there is no problem, but M2 is now red, because from left to right traffic is no problem, from right to left I cannot allow traffic, because I have to allow the traffic from main to side. That means I need to allow for this turn. If you want to allow for this turn, I need to block this traffic. That means I become M2 should become green, red, M2 should become red, M1 will continue to be green, MT will now become green. From red, red it will become green, so that the traffic will be allowed. Side of course remains this light, again we cannot allow the traffic from side to the main in this direction, you cannot allow it. So, it continues to be red. So, side red, M2 red, MT green, M1 green. This period, this is the third state in which this circuit will be found, this traffic light controller will be found, this is third state. And how long do you want this turn signal to be on? That is called TTG, I am calling it. TG stands for turning green, turning signal green, T is the time. Time for which the turning signal green is called TTG. So, for the period TTG, these conditions will prevail. At the elapse of TTG, at the end of TTG, what will happen is I should stop this traffic from side to red, side to main to side, and let the other side street, this side street traffic back into the main. So, originally I allowed from main to side, now I should allow from side to main. So, TTG has to be turned off or made green, and S should be made, this should be made red and this should be made green, but I can't make it red directly from green, we have to go through yellow. So, this state fourth is main turning signal in the main road, will be yellow. M1 is yellow. Why am I making M1 yellow? Because unlike in the case where the traffic from main to side is organized, because I am assuming that the main street is flowing like this, it is a side lane. So, it is a two lanes of traffic, and those who want to turn are already standing here in a separate lane. I need not stop this for letting this on. On the other hand, when I am turning from here to here, I cannot let this happen here, because we do not know the how well these lanes are in this state. Supposing these lanes are not well defined, there is a possibility that this traffic coming from the side road into the main road may collide with the traffic which is going directly from main road from left to right. In order to avoid this, while I am allowing this traffic to continue when this is allowed, I am not allowing this traffic to continue when this is allowed. So, from main to side, I am allowing the main street traffic from left to right, whereas from side to main, I am not allowing the main street traffic from left to right. That means I do not want this happen, which means I should not only make this MT red, I should also make M1 red. The main should be red, T should be red, but blue cannot be both made red immediately, they have to go through yellow. So, this state makes M1 yellow, M2 yellow, this continues to be red, of course, this continues to be red. This is the condition in which there is a warning to the main road users whether they are directly going or turning. Now, the light is going to be switched off to red. So, be careful, either stop, prepare to stop. So, that condition is called state condition 4 or state 4, which will again last for the period of T yellow. I am not again distinguishing between the yellow timing on the main street or the side street or return signal. So, T yellow is the time period I am allowing for this condition to elapse or to for this Ty is the time for which I am allowing this condition to last. So, after the end of this Ty, main one will become red, so that main street traffic from left to right will be halted. M2, MT will be stopped, the traffic from left to right which also going into turn, that also will be stopped. So, M1 is red, MT is red, M2 is already red, no problem. Now, side, now we are now made way, this is stopped, we are allowing traffic from side to red. So, side to red is allowed, that means side becomes green. All the while I am allowing this free traffic from side to main on the left hand side, there is no problem, side to left on the main side. This is not being hindered by anybody, it is always on. So, what is called free left in our traffic parlance, in our system, in our roads. When you say free left means you can always turn without having to wait for any signal. Of course, you have to make sure that there is it is safe to turn. Make sure that there is no traffic is coming onward, that you will not collide with anybody or any vehicle. As long as it is safe, you can turn without having to wait for a signal. Such a condition is somehow we call free turn or free left in our parlance. I find this peculiar coinage in our traffic light control in our cities in India. Anyway, so we have the free left here, free left, free left, free left, free left, free left. Here this is free left, but not here. Once this is not a free left anymore, because this red is M2 is controlling not only direct traffic, is also the side traffic, main to side, from right to left main and right to left side, both are controlled by M2. So, it is not free left. When this is on, this can also go, when this is on, this can also go. When I am stopping this, this also cannot happen because I do not want this to go on collide with this. Similarly, when I am stopping this, this cannot go. Now, at the end of Ty, as I said, now side is green, this is only traffic allowed apart from the free left here. This road cannot, this traffic cannot go farther, cannot turn, this traffic cannot go farther, cannot turn. This is state 5. And this will last for a while where we want to prepare, it depends on the time we want the side green to be active. So, decide what is the period for which the side green is be on. So, when SG is on, this will be like this. At the end of the period SG, we call it TSG, time for which the side is green, TSG. We will go back to this condition where we will have to prepare for to make this red, that means the side to main will have to be halted, and we have to let this traffic flow freely in both the directions, because that is the condition which we want most of the time. So, for that what I need to do is to make side red, but side cannot be made red abruptly, it has to be made red first, it has to be made yellow first and then red. So, this condition we have this continues to be red, this continues to be red, this continues to be red, but side becomes yellow. Once this happens, we know that this side road traffic has to stop. Once it is yellow, the traffic here will have to prepare to stop. So, at the end of the period of Ty, after Ty, we go to 1. 1 is what? 1 is when left to right traffic is allowed to the main street, right to left traffic is allowed to the main street, no turning is allowed from main to side, no traffic is allowed from, no turning is allowed from side to main, but this free left and this left, these are allowed. That is correspond exactly this state. This S1 state is nothing but main, left to right, main, right to left, this traffic not allowed, and this traffic not allowed. This is allowed as I said always, and this is allowed as long as this is. This turn is allowed as long as this turn is, this traffic is allowed. So, 6 states under which in which this circuit can exist. This problem is a example of how a specification has been translated into a state machine. A state machine means a state diagram, and for that I need a very clear understanding of the problem. These figures give a very good understanding of the requirement. What are the various inputs and outputs? Inputs are Ty, the yellow time, TMG, main green time, TTG, turn green time, TSG, side green time. So, Ty, TMG, TTG and TSG are the 4 inputs to the system. What are the outputs? Each light, M1, M2 the main lights, MT turn light, S side light, each of them can have a green, yellow, red. So, these are the outputs. So, there are 4 lights each with 3 combinations and 4 outputs. These are the inputs and outputs, and the circuit can exist in various conditions and move from state to state depending on the conditions. That becomes a state graph, and once you have a state graph, you know how to implement it. So, the problem translation, the translation is the problem from specification, word description as they call it, from a clear description of the problem in words, in English sentences, to drawing of the state graph is the most critical thing. Once that is done, the rest is easy because we know the procedure, how to do implementation using standard techniques. We can use gates, we can use multiplexers, we can use ROM, PROMs, we can have PLAs, PALs, we can use flip flops for state variables, or you can use a register, you can use a shift register, you can use a counter, whatever. So, this is the algorithm they call it. So, this is called algorithm, they call it. Algorithm is the procedure, the step by step operation, the sequential operation. These diagrams are only an illustration to help us to understand the problem. The word problem is translated into this. This is the sequence of events. This sequence of events is a description in an algorithmic sense. If those of you are familiar with programming, computer programming, you will call it a code, a program. It is not a program in the sense it does not use syntax of a particular language like C language or anything. It is looks like a program, but it is not a program. You can call it a pseudo code if you want. A pseudo code. Pseudo code is a program, but not using a syntax of any particular language. It is an English description. Or you can also call it a algorithm. What is an algorithm? Algorithm is a step by step. Algorithm is a step by step behavior of the circuit based on the various conditions of input and what conditions of output are possible. So, what are these steps again to go through? Normally the circuit is with main 1 green, main 2 green, main turn red, side red. This condition allows for a period called TMG, main green time. At the end of main green time, this M1 continues to be green, M2 turns yellow to start stopping the traffic from right to left on the main state. MTR, turn signal is still right, still red, side signal is still red. Then you allow this condition for a period called yellow, T yellow, which is uniform for all the yellow lights, even though main yellow is normally more than the side yellow, but we are keeping it equal to make it simple. After the period of T yellow, main 1 continues to be green, that means left to right traffic is allowed, but right to left traffic is stopped, M2 it becomes red. MTG, turn light is allowed. Turning traffic from main to green main to side is allowed by a green light. Side red, that means turning traffic from side to main is not allowed. This condition will last for a period called TTG. TG stands for turn green. The period for which it is green is called TTG. After the elapse of TTG, I have main 1 yellow, main turn yellow. I am going to stop the traffic from left to right on the main state and also the turn traffic from main to side to allow the side to main traffic. In order to do that, I need to go through an yellow sequence. So, M1 yellow, M2 MT yellow, M2 continues to be red because the traffic from left to right to left is still not allowed, because once there is a side to main traffic, I cannot allow the traffic, this traffic I cannot allow this traffic from right to left. Continues to be red, side traffic is still red, of course we have not cleared it. This condition provides for a time of Ty, the time for which the yellow signal is defined. At the end of Ty, both the main 1 and the turn signal from main both become red. That means we are cutting off the traffic from left to right as well as cutting off the traffic from main to side. M1 red, MT red, M2 is anyway red, side is allowed green. That means the first time and the only time side traffic is allowed. And this condition will exist for a period of T SG. SG stands for side green and T stands for time. TSG is time for which the side is green. At that period, side green will have to become yellow and become eventually red. So, after this period, side becomes yellow, so that we can become red later on. But since it is still yellow, traffic is not completely halted. So, I cannot allow any other traffic to any other light to change. So, M1 has to continue to be red, M2 has to continue to be red, M2 has to be M2 has to remain M2 has to continue to remain red, side will become yellow, and this condition will last for a period of Ty. Ty stands for the yellow light period, in this case from side to main. So, after Ty we go back to 1, which is our first primary interest, main 1 green and main 2 green, both directions traffic, no turning on this side, no turning on this side. So, this is the algorithm, you can call it algorithm. Algorithm is a procedure, a step by step procedure of the events, of the behavior of the circuit. Pseudo code is people use it because the pseudo code is something like it looks like a program, computer program, but it is not a program in any sense, because program requires some syntax for a particular language, C language, it is not that, C++, it is not like that, but really it is a sequence of events that take place, and each of these sequences correspond to one state of the machine. So, we have a state machine in which the circuit has to exist in each of these states, and they go from each one of these states to another state based on certain input conditions defined by the timing Ty, TTG, TMG, TSG. We can put additional conditions like pedestrian switches, traffic flow conditions by sensors and all that, but we are not doing all that now in this case to make it simple. So, how is the state graph going to look like? First of all, let us see the state graph is first of all you have to see whether the state graph is a Moore graph or a Mealy graph. This is a Moore graph. Why is it a Moore graph? Moore graph defines outputs for states. Mealy graph defines outputs for state and a particular input combination. In this particular case, states define the outputs. The circuit can exist in all these 5 states or 6 states, 1, 2, 3, 4, 5, 6, and each state outputs are frozen. These are the outputs. So, when the outputs are given fixed corresponding to states, there is a Moore state graph. So, we already said that there are 6 states, S1, S2, S3, S4, S5, S6. In S1 the circuit remains, there is a timer which goes, this timer is called MG, TMG. As long as TMG is not elapsed, is not over, the circuit remains in this state. TMG can be several clock cycles. See, the clock cycle is different from these state cycles, because once this circuit need not be very high speed circuit. When you try to decide what clock, what frequency the clock should this circuit operate, need not be very high. It is not like a Pentium processor or anything. We are talking about traffic lights which change slowly. We talk of at least 1 minute for the main street green and about 30 seconds for the side street green, and yellow maybe 10 seconds, 15 seconds, 20 seconds depending on the conditions. So, when you are talking about that, this frequency at which these circuits have to work, the clocks have to be fed for these circuits need not be very, very high, but still it will be several clock cycles in each of these timing intervals, because we will have a timing interval which will be several clock periods of the clock that we feed as a system clock. So, you have a system clock which is counted, and when a particular count is reached we will call it TMG. So, we define for this given time, depending on the time TMG let us say is 1 minute 60 seconds. Assuming you have a clock period of 1 second, which is too large, I am just saying for example, 60 such clock cycles will exist because for TMG. So, you keep counting, when 60 counts are reached, TMG becomes on. When TMG becomes on, the circuit goes from this state to this state, that is what I mean. So, there will be a system clock and a counter. The counter counts the system clock and comes up with these values TMG, TTG, TSG, TY. These are the signals that are used as these signals. This can be several clock cycles of the system clock, which can itself be very, very small clock, very low frequency clock, need not be very high. So, we have S1, the circuit remains in S1 until TMG is reached. When TMG is reached, it goes to S2. S2 is the yellow state. So, it will remain in S2 until Ty becomes high. Until that time, when Ty is not there, it remains in this state. So, this is the main green, this is main yellow. Then when it is over, we go for the turn signal. So, it becomes turn green. After Ty, the turn signal becomes green. So, TTG is the period for which it is going to be green. So, until TTG elapses, the circuit remains in S3 state. After TTG, it goes to Ty, it goes to S4. S4 is again yellow state, correspond to that light. The turn signal light has to be yellow. That time is called the Ty. So, in S4 it remains until Ty is reached. Until Ty is reached, it remains in S4, Ty bar, and then it goes to TSG, side green. So, side green will last for a period called TSG. So, in S5 the circuit will remain as long as TSG is not reached. When TSG is reached, it goes to S6, which is yellow state for the side light, side yellow. So, if that is condition is Ty, this is as long as Ty is not reached in S6, it will continue to be a side yellow, and at the end of Ty it goes back to S1. So, this will repeat. So, this is my state diagram with inputs, as I said, TMG, TTG, TSG and Ty. Outputs are already defined. Each of these output states S1, S2, S3, S4, S5, S6, I have already defined the outputs here. For example, in S1 the outputs are M1G, MTR, M2G, SR. In S2 the outputs are M1G, MTR, M2Y, SR. So, outputs are not drawn. Normally in a Moore circuit I should write the outputs in the states, because the states circles are too small, and I have already used this to write the state label. I do not have space to write all the list of outputs in each of the states, but we know we have already listed them there. So, this will do. This extra state I have here, do not worry about it. This will do. It goes on repeating in 6 states, assuming it goes forever. But normally in any condition, any practical design problem, we do not design for something to go on forever. There is always an interruption, a power supply failure, or the power is switched off in the night, or some resetting condition exists because of some, you want to stop the traffic light for some reason. So, what we can do is, there are a couple of things. Suppose there is in the night you do not want the supply to be on, you can switch off all the lights, in which case there is a master switch where all the lights are off. But there is nothing like off here, because there are only 3 lights, green, yellow, red. So, all of them should be off, the power should be off. So, you can switch off the power, or you can define a state called initial state, in which you can have a blinking red, something like that. Now, you might have seen it in busy streets at the end of the day, at the night, late in the night, you will see in the main street this yellow will blink, that means proceed cautiously, and in side streets red will flash, saying that stop and go. When you see a flashing red light and we are trying to enter from a side street to a main street, The red flash red indicates that you should stop, look for the traffic in both directions and then only proceed. If you see a flashing yellow in the main state, you know a side street is approaching, there may be a traffic there, be watchful, so proceed cautiously. That is a blinking yellow. So you want to put all those conditions. You can introduce an extra state called init state. This could be the state in which the circuit is switched on for the first time, because we are going to finally have flip flops to implement. So the flip flops can be 0 or 1, whatever combination. So you will find them in any of these combinations. So make sure that as soon as you put a reset state, from that state it goes to S1. So this initial state is an optional state, you do not have to have it. Initial state you can have some blinking condition or whatever condition here, remember it goes here. So this is the state graph with 3 variables, because there are 6 states. Leaving out the init. Without this there are 6 states, that means 3 variables, 4 inputs in addition to state inputs, and 12 outputs, 4 lights each, 3 colors. But actually these 12 outputs, some of them are redundant. For example, some lights are complement of other lights. So you can make some simplification on these 12 lights, you can remove, but then finally the lights are there, 12 lights are there. The logic of one light may be complement of the other. There is no need to have sometimes separate lights. Sometimes you can have the same signal going from for 2 different lights if one is a complement of the other. But I am not taking all that into account right now. Right now I am looking at the bare state graph, saying there are 4 inputs, 12 outputs, 6 states. 6 states requires 3 variables, that means 4 input variable plus 3 state variables. So you can have a combination of, my combination logic will be A, B, C are 3 state variables, 4 inputs variables, TMG, TTG, TSG, TY, and then 3 output variables. And then these 12 outputs, M1 green, M1 red, yellow, M1 red, etc. 12 light outputs. You know, I can implement it using combination logic, flip flops and combination logic. This combination logic can be gates, multiplexers, proms, or you can put the whole thing in a PAL, programmable array logic. So if it's a prom solution, the size would be, it's a prom 2 power 7, 12 plus 3. I am assuming no reduction in the signals. If I can combine some of these outputs, I can reduce the size, but I do not want to really do it. Without doing any compression, compaction of the outputs, I have 12 outputs for this and 3 for here, 15 outputs, 4 plus 3 is 7 inputs. So 2 power 7 into 15 bits is the size of the prom, plus 3 D flip flops can do the job. We can look at some of the other implementations next lecture.